last time we've looked at the structures of solids, defects in solids, we've looked at ionic bonding, and we were introduced to band theory in terms of metallic bonding. This time we'll partially complete our discussion of the tetrahedron of solids by looking at covalent bonding in network solids, and we'll mention a little bit about molecular solids. So here are two examples of covalent network solids. This is the diamond lattice, where in the case of these atoms as carbon, this is the structure of diamond, and you see that each carbon is bonded to 4 other carbon atoms in a tetrahedral geometry. And then this carbon is bonded to 4 other atoms, this carbon is bonded to 4 other atoms, so this creates a 3-dimensional network of covalent bonds. And diamond is a very good insulator, so that we'll explain the bonding in a covalent network in the next slide. And this structure here is another form of carbon, graphite, where it's a covalent network solid. Each carbon atom is bonded to 3 other carbon atoms in a 2-dimensional network, and there are these layers of carbon atoms are attracted to each other by van der Waals forces. So here we see why we have this tetrahedron of bonding rather than just 4 different categories, that there's a continuum between a pure network solid, such as diamond, and a pure molecular solid, such as sugar. Somewhere in here is graphite, which has both a covalent network and intermolecular or van der Waals forces holding the solid together. So the diamond is an insulator. Its conductivity, we defined conductivity in the previous lecture, at room temperature is about 1 × 10⁻⁶ Siemens per centimeter. Graphite has some conductivity. Along this direction, because these carbons, we can consider them to be sp2 hybridized, and so there's a p orbital, there's a pi network similar to that polyacetylene pi network we saw before. But in this direction, there's only van der Waals attractions. It's hard for the electrons to travel. So graphite would be considered a weak conductor, and it's in only a particular direction. So if we get to a larger compound, say silicon, silicon has the same structure as diamond, with silicon tetrahedrally bonded to other silicon atoms in the solid, but silicon has a higher conductivity. So how can we explain that? If we look at the bonding between silicon atoms in the covalent network, we can consider them sp4 hybridized, and so here I've drawn the sp4 hybrid orbitals on the silicon atom, and in this would be a sigma bonding network, sigma bond, sigma bond. There is some overlap between the negative lobe of the sp3 orbital and this bond here, so that would slightly increase the energy for this type of bonding arrangement. If we look at another type of silicon bonding arrangement, we have still bonding sigma bond, we still have a sigma bond interaction, but this sigma bond is out of phase with this sigma bond, which then creates positive overlap here, and so it would be slightly lower in energy than this sigma bond neighboring interaction. So in the three-dimensional network, instead of having just pure sigma bonds and pure sigma antibonds, there is some spreading of the electron distribution energy levels into, again, a band, where we have slightly higher energy bonding interactions and slightly lower energy bonding interactions. So this spreading of the states, energy states of the electrons in silicon, isn't as broad or wide as in the case of a metal like sodium or magnesium. And so these two states from the sigma bond and the sigma antibond, these two bands don't overlap. There's actually a gap. You can call that a band energy gap, or E sub G, between the filled band and the empty band. The filled band we would call the valence band. It's made up of the valence atomic orbitals of the silicon, whereas the empty band we could consider the conduction band. If we were to place an electron in this empty band, it could easily move among the bonds because there are no other electrons to inhibit it. So this gap is smaller for silicon than for carbon in the same structure, diamond lattice, and so we can distinguish between an insulator and a semiconductor by looking at this energy gap. If the energy gap is greater than the thermal energy at room at temperature, then it's an insulator. And we see that KT, that's that Boltzmann constant, because just like we saw with metallic bonding, these electrons can gain thermal energy and get excited, and the population then of that energy distribution of the electrons is determined by the Boltzmann distribution. So you see here that some of these electrons are trying to get excited, create holes here in the filled band, but they don't have enough thermal energy to actually bridge the gap to get up into the conduction band. So that would be the case of an insulator. On the other hand, if the band gap energy is smaller than the thermal energy available at the particular temperature, then some of these electrons will gain enough energy to reach the conduction band and create what's called a semiconductor. So again, if this gap was smaller, say we were to change the system in some way, maybe change the atoms, go down from silicon to germanium, so we have a smaller band gap, then now you see that at this Boltzmann distribution, some electrons get excited up into this empty conduction band, causing it to conduct a little bit, a semiconductor. So that's the case of an intrinsic semiconductor. We can, besides changing the atoms, we could change from one element to another. We could also make a compound by mixing different elements. So here we have an example of, let's take some arsenic and add it to the silicon lattice. So we have the three-dimensional silicon diamond structure, and we replace a few silicon atoms with an arsenic atom. So this is a type of non-stoichiometric compound. And this is also what we call doping. So when we replace the silicon with an arsenic, arsenic has a similar size to silicon, so it can fill the silicon place in the lattice without changing the lattice too much. But it has extra valence electron. That extra valence electron can be donated into the silicon covalent network, and then hop or conduct throughout three-dimensional structure. So this is called a donor level, where that arsenic valence electron energy level is, and it can go up into the conduction band and create a conductive material. On the other hand, we could add gallium. Gallium similar size to silicon, so it doesn't disturb the three-dimensional lattice very much, but it has one less valence electron than silicon, and so it will remove an electron from silicon, leaving a hole, positively charged hole, that can then also hop through the three-dimensional network. Moving charge is conductivity. So here we see the gallium acceptor level, the gallium empty valence atomic orbital, ready to receive an electron from the filled band, creating holes in the filled band that then can move and create conductivity. So by changing the elemental composition, we can tune how much conductivity we have in the system. So that's, again, a semiconductor, which we can adjust by doping. I guess I should also point out that another way to classify these is that this is an N-type semiconductor because it's a negative charge that's moving, whereas this is a P-type semiconductor because it's a hole or positive that's moving. And as you'll see when you apply this information, we can build devices by combining N-type and P-type semiconductors. Now finally, let's discuss a third class of material. So we've looked at metallic bonding, we've looked at insulators, semiconductors, so I guess actually this would be a fourth class of material. So to review so far, we looked at, we discussed conductivity, but let's look at this in terms of resistivity, which again is the inverse of conductivity. And let's look at that versus temperature. For metals, we mentioned that the conductivity decreases with increasing temperature. So that means the resistivity is going to increase. Semiconductors, as we increase temperature, we increase the population of higher energy electrons, and so our conductivity will increase. So our resistivity decreases with temperature in a nonlinear fashion. That's an exponential relationship. So a semiconductor, as we increase temperature, the resistivity will decrease. In the case of a superconductor, as we increase temperature, it increases, so it's like a metal that way. But if we decrease the temperature enough, we reach a point where resistivity drops to 0. This is the critical temperature for this superconductor. And to explain superconductors, the first superconductors were discovered by cooling metals. As you can see, they have the same type of trend as metals. And it wasn't until much later that theory caught up with this to explain why metals work this way, and superconductors work this way. BCS theory, developed by Bardeen at U of I, Cooper, and Schrieffer, stated that electrons are moving through this superconducting state as a pair. So far, when we looked at metals and semiconductors, we saw the charge carriers, whether they're holes or electrons, moving through the system alone. These pairs in a superconductor, also called Cooper pairs, would be spin paired. So since they're negatively charged, they wouldn't be attracted to each other, but if you pair them up, you can put electrons in the same place at the same time. And then as they move through the structure, they help each other by distorting, one electron distorting the structure, creating attractive, positive situation that will then attract the next electron. And so the electrons don't get scattered like they do in a metal or a semiconductor as they bounce around in the atomic network. So that explained the first type of superconductors. Since then, high temperature superconductors have been discovered, and we worked with those, explored those in our lab. So we learned about semiconductors, insulators, and superconductors in this lecture, and this concludes our section on bonding in solids.